Imagine, just for a second, the absolute most stunning photorealistic CGI you've ever seen on screen. You know the kind, the way the light bounces perfectly off a car's hood, or that soft, incredibly lifelike glow of skin in a high-end digital portrait. It looks completely real to our eyes, right? But what if I told you that right beneath that beautiful illusion of perfection, the actual physics being simulated are, well, they're incredibly simplified. Now I want you to imagine taking that slick, modern CGI and just smashing it together with the chaotic, microscopic, and totally unpredictable reality of quantum physics. So what actually happens when you mix standard computer graphics with the quantum realm? That is exactly the fascinating question we're going to explore today.
Welcome to this explainer. Today, we're unpacking a truly mind-bending paper that was published in June of 2026. It's called Rendering Coherent Scattering via Quantum Collision Models, and it's authored by this brilliant team of researchers, Juan S. Ferreira, Spencer S. Topol, Pierre Fromholz, and James R. Wooten. What they've proposed here, it isn't just some minor incremental update to how we render digital light. No, it is a fundamental reimagining of light-matter interaction in computer graphics. They are literally bridging the gap between theoretical quantum mechanics and the actual pixels on your screen.
To really understand why this paper is such a huge deal, we have to look at how things are currently done. Historically, rendering engines treat the optical properties of materials as completely static. But as we all know, real life isn't static. So the absolutely crucial point here is that this traditional assumption completely breaks down the moment a material's properties dynamically evolve in response to the light hitting it. The researchers' new framework introduces a system where those optical properties are dynamic. They're reacting, they're changing as illumination interacts with them, exactly like they do in the real physical world.
Okay, so here is our roadmap for how we're going to break this complex physics paper down today. First, we'll look at the CGI lighting problem. Second, we'll enter the quantum realm. Third, we'll cover the quantum collision model. Fourth, we'll talk about pre-computing the chaos. And finally, we will explore rendering impossible materials.
All right, let's jump right into Chapter 1, the CGI lighting problem. To really appreciate this new solution, we first need to understand the limitations of the tools that digital artists and rendering engineers have literally been relying on for decades. And it all comes down to how we fake reality. The foundational flaw in current rendering is the strict assumption that a material's optical properties never change. In classical computer graphics, when light hits a digital surface, the computer basically just looks up a fixed set of rules for that material. It says, okay, right, this is plastic, so it reflects exactly this much light in this one specific direction. We're essentially faking these optical properties by treating them as static data points. But light in the real world, it's dynamic, it's messy, and materials can actually change their optical state when they get bombarded by photons. The researchers point out that traditional techniques just completely ignore this dynamic evolution.
Which brings us to Chapter 2, Enter the Quantum Realm.
To solve this massive limitation, Ferreira and his team had to look way beyond standard computer science. They dipped right into quantum physics to propose a totally novel shading framework. But here's the cool part. They aren't suggesting we just throw away everything we know. They're not ditching classical ray tracing, which is, the standard method we use for simulating light rays bouncing around a 3D scene. Instead, they're enhancing it. They are combining classical ray tracing with a quantum collision model. Think of it like a tag team. Ray tracing does the heavy lifting of getting the light to the surface of the object, and then the quantum collision model takes over to explore the effect of coherent light-matter interactions. It is the ultimate crossover between classical geometry and quantum mechanics. Now, to make this actually work, the authors introduce the concept of quantized modes. In traditional rendering, light is just a vector, right? It's a line with a color and a brightness value. But here, the researchers treat incident light and material excitations as quantized modes. That means we're no longer looking at light and materials as flat data points. Instead, we're looking at them as tiny, discrete, interacting pieces of quantum energy. The light brings its own quantum state to the table, the material has its own quantum state, and when they meet, they interact in this highly complex, completely dynamic way. Let's move on to Chapter 3, the quantum collision model. You can visualize this entire process almost like a microscopic quantum pinball machine. It happens in 3 steps. Step 1, classical ray tracing brings the light rays directly to the digital surface. Step 2 is the moment of impact. The light and the material's excitations are treated as those quantized modes we just talked about. And finally, Step 3, and this is where the magic happens. The light doesn't just bounce off, it enters the material.
The authors model this subsurface scattering as a sequence of symmetry-constrained unitary collisions. So just imagine the light particles experiencing this rapid, highly complex sequence of collisions inside the material, with each single collision altering the state of both the light and the material itself based on very strict quantum symmetries.
And this brilliantly illustrates why this approach is so groundbreaking. There's a line in the paper that perfectly captures this, stating that the formulation allows for the incorporation of chaotic optical responses due to multi-layer interference effects. Basically, because they're using a quantum collision model, they can finally account for non-integrable dynamics, which is really just a fancy way of saying math that is way too wild and complex for traditional renderers to handle. They are capturing the wild, messy, real-world physics of light bouncing around inside multiple microscopic layers, interfering with itself, and creating these chaotic, yet mathematically accurate visual responses.
Okay, let's look at the practical side of this in Chapter 4, Pre-computing the Chaos.
Now, you might be wondering, wouldn't trying to simulate real-time quantum collisions for every single pixel on a 4K screen literally melt any computer on Earth? And yeah, you'd be absolutely right. But the pragmatic twist of this research is that these massively complex collision operators can actually be pre-computed. And the best part? They aren't waiting for some distant, futuristic sci-fi technology to do it. They're using near-term quantum computers to do the heavy mathematical lifting today. By running these quantum collision models on actual quantum hardware beforehand, they can capture all that chaotic dynamic behavior without having to try and calculate it live while the frame is rendering.
So where does all that pre-computed data actually go? It gets packaged into a BSDF, or a bidirectional scattering distribution function. If you're not familiar, this is just the standard mathematical format used in computer graphics to define how light scatters off a surface. The absolute genius of this workflow is that these chaotic quantum behaviors are calculated on quantum computers and then neatly baked right into standard BSDFs. What that means for us is that you can plug these wildly complex quantum-simulated materials straight back into normal, standard rendering engines. You get all of the visual benefits of real quantum physics, but you don't actually need a quantum computer sitting on your desk to render a video game or a movie.
Which brings us to our final stop, Chapter 5, Rendering Impossible Materials.
Let's quickly summarize the key takeaways we've covered. This new framework seamlessly integrates with standard BSDFs, making it incredibly practical for today's pipelines. It utilizes near-term quantum computers, proving that quantum applications in computer graphics are literally here right now. But honestly, the most exciting part are these last 2 points. This technique enables the generation of entirely new, physics-inspired materials. Because we are no longer bound by static, faked data lookup tables, we can create materials that possess distinct optical signatures that have never been seen in computer graphics before. We are talking about rendering materials that react to light with a level of chaotic realism that perfectly mimics the true complexities of the physical universe. Which leaves us with this final thought to ponder. As this technology scales up and these quantum collision models become even more detailed, we are moving away from merely faking reality to actually simulating the quantum foundations of light and matter directly on our screens. So what will a strictly physics-inspired, quantum-rendered world actually look like? Well, if this paper is any indication, it's going to be far more dynamic, beautifully chaotic, and breathtakingly realistic than anything we can currently imagine. Thanks so much for joining me on this explainer, and I hope this deep dive into the quantum side of computer graphics has completely changed the way you look at digital light.